Hi mathematicians, this is the review for limits, continuity, and differentiability. We're going to go through hopefully all the problems on here so that if you were struggling in something you might be able to pick something up there. We're going to start off with the big ideas that hopefully you have somewhere in your brain, and if not, somewhere in a notebook that you can keep track of this. For a limit to exist at a point, visually, a graph has to approach the same value from both sides. It doesn't matter what happens here. So that could be anything going on there. Algebraically, what we're saying is that the limit from the left, as we approach a value, let's call that a, of some function, must be equal to the limit from the right, as we approach that same value of a, of that function. This just means that the limit as x approaches a of f of x exists. And it would equal what I can't spell today. It would equal whatever those things were equal to. For a function to be continuous at a point, this goes one step further. Graphically, we're saying that not only do we have to approach this unknown thing that's happening here, but we've got to have that point filled in. In other words, not only does the limit have to exist, so as x approaches a from the left, must equal the limit as x approaches a from the right. That must also equal the same value of the function at that point, or f of a. So in other words, we're not dealing with a random point sitting up above or sitting down below or just not there at all. We have to have that point in place at the same height. If all three of these things exist, we can say that it is continuous. The last piece, and again, this is branching off what the previous two say, if we are continuous at a point, so in other words, if we've already established the stuff up above, so if we are continuous at x equals a, differentiable means that the derivative from the right is equal to the derivative from the left. We're approaching the same slope of both sides. We could do this using definition derivative, or we can use some less lovely notation, which is saying that the derivative from the left of f of x at x equals a must be equal to the derivative from the right of f of x at x equals a. And ideally we use some kind of better notation for this, but this will do for now. And then we go to apply this stuff. So we're going to go piece by piece. Does the limit exist at x equals 1? I'm going to look at both sides. Sorry, x equals negative 1. We'll look at both sides. And when I plug in these values, so the limit as x approaches negative 1 from the left, I'm going to use the stem x squared minus 2x plus 1. When I plug that in, we get negative 1 plus 2 is 2, plus 1 is, sorry, negative 1 plus 2 is 1, plus 1 is 2. And then we do the limit as we approach negative 1 from the right side of 3 minus x. 3 minus negative 1 is 4. So no, the limit does not exist. If the limit does not exist, then no, it is not continuous, because the limit as x approaches negative 1 of f of x does not exist. And if we're not continuous, no, we are not continuous at this point. Which is weird because this should not have come out that way. And sometimes I need to stop myself when I'm plugging things in on the fly because this is certainly not equal to 2. This is equal to 4. And because of that, my first statement should have been yes. And because of that, we can ignore that second statement and then jump to continuity, where we find f of negative 1, which is 2. And now, since that point is not equal to the limits from both sides, so up here we got 4 from both sides, but here we've got 2. Now it's not continuous. And then we can use the same reasoning to say that it's not differentiable. Alright, same thing going on for number 2. Does the limit exist? We're going to check from the left and from the right. So the limit as x approaches -1 from the left. We're going to use that, and we've got it's going to be x squared minus 5, which is 1 minus 5 is -4. And the limit as x approaches -1 from the right. We're going to use that one. We get x plus 2, so -1 plus 2 is 1. No, the limit does not exist. No, it is not continuous because the limit does not exist. And no, it is not differentiable because it is not continuous. For number 3, at x equals pi, so we're going to take limit from the left. So the limit as x approaches pi from the left. That'll be this guy. And cosine of x, that equals -1. Then we got the right side limit going on. So the limit as x approaches pi from the right, and that's going to be of x squared minus pi x minus 1, which is pi squared minus pi squared minus 1, which is -1. So the limit does exist. I'm going to check to see if it's continuous by finding f of pi, and that's going to be the first one since that has the equals part. And we already found that that's -1, so yes, it is continuous. For differentiable, we've got to take the derivative of both sides. So the derivative of cosine of x is going to be sine negative of x, and the limit as x approaches pi from the left for that guy is going to be 0. And then from the other side, the derivative of the pi squared minus pi x minus 1, well, pi squared is a constant, so that's 0, minus pi for minus pi x, and then 0 for the last part, and that's going to be -pi. So no, it is not differentiable because the derivative from both sides is not equal. Okay. Moving on to number 4. It says that the function is differentiable at x equals 3 and define the values at k and n. This means that the limit has to exist, it has to be continuous, and then the derivatives have to be equal. So the first thing I might do is to find the derivative, because I know I'm going to need to. And for the left side, that's going to be k over 2 times the square root of x plus 1. That's using the power rule. And then for the other side, 2 is going to be 0, and mx is just going to be m for x is greater than 3. Okay, so I guess for the first part, I might as well, while I have the derivative here, just do it out. So that means that k over 2, 3 plus 1 is 4. K over 2 times 2 has to be equal to m. So k equals 4m is going to be an equation. We're probably going to get another equation from my limit part. And if we do limit from the left, so that would be k times 2. And the limit from the right is going to be 2 plus and then 3m. Okay. Well, I've got a k I can plug in because I've got k equals 4m over here. And when I do that, we get 8m is equal to 2 plus 3m. So we're going to have 5m equals 2 and m equals 2/5. If I plug that in to find k, we get k is equal to 8/5. Okay, moving on to the next one. We've got sine inverse of x minus 1 ln of x plus pi over 2. Okay, first thing I'm going to do is to figure out the derivatives, although I guess I know that if we're looking at 1, I might as well do the limit part first. In my head, I had to find k's and m's, but there are no k's and m's here. So the first thing we're going to do is find the limit from the left, limit from the right. Oof! That's what happens if I just jump from problem to problem. So the limit from the left at 1 of sine inverse of x is going to be sine inverse of 1, or pi over 2. The limit as x approaches 1 from the right of ln of x is going to be ln of 1 plus pi over 2. ln of 1 is 0, so the limit exists. F of 1, we're going to use the bottom one, which also happens to be pi over 2 because we just solved that. Okay, now we got to do the differentiability part. We're going to check the derivatives, and we're going to start with the derivative of sine inverse of x. So I'm going to start with this. So we got sine inverse of x. That also means that sine y is equal to the x value. And if I draw a triangle with an angle of y, we know that sine is the opposite over hypotenuse. In other words, x over 1. That means that this third side is going to be 1 minus x squared, square rooted using the Pythagorean theorem. And that if I needed it for some strange reason, for example, I don't know why I might possibly need this, cosine of y would equal the square root of 1 minus x squared over 1. Okay. Now I'm going to keep going with this. So the derivative of sine of y would be cosine of y times y prime, and the derivative of x is going to be 1. Dividing by cosine of y, which we're going to substitute this guy in for, we get y prime is equal to 1 over the square root, 1 minus x squared. So derivative-wise, we're looking at 1 over the square root 1 minus x squared. And if we plug in 1 for that, we get 1 over 0, which does not exist because it's undefined. Therefore, the derivative cannot be differentiable. But just in case you're curious about what these graphs might look like, I got a picture for you. And I'm pulling that up now, so bear with me for a second. Okay, and you can see where the red graph joins the blue graph. These graphs do not meet at the same slope, although they do meet, which is why the derivative does not exist there. Also has an issue where the derivative goes to infinity for the inverse sine because we have a vertical tangent line there. Alright, so now I've got to find m and k again. We start with my limits. The limit from the left is going to be m plus 2, the limit from the right is going to be 0. Therefore, m equals -2. Take the derivatives. The derivative from the left is just going to be m. The derivative from the right is going to be k over x at 1, which is k over 1. And that means that m equals k, so that k equals -2 also. So that's going to work out quickly. Looking at number 7, the limit from the left is going to be -2m minus 5. And from the right, that's going to be 4k plus 1. For the derivatives, that's going to be m is equal to 2xk, and that'd be -4k. So if I plug that in, we've got 8k minus 5 is equal to 4k plus 1. We get 4k is equal to 6, which means that k is 3 over 2. And that would also mean that m is going to be -6. Doing the same thing here. From the left side, e to the 0 is 1, so we get k. From the right side, plugging in 0, we get 3. That's nice. Do the derivatives, we'd get 2k e to the 2x, which is going to go away again when we plug in 0. And from the right side, we get -m. So 2k equals -m. That means that m would be -6. For number 9, plugging 2 in, we're going to have 2m minus 2. And for k, 4 minus 3 is 1. That's just going to be k. Taking the derivatives, that would be m equals, and then the derivative of this lovely mess is going to be k over 2 square roots of x squared minus 3 times 2x for the chain rule, plugging in 2. So that's going to be, those cancel, 2k over 1. Nice. Okay, maybe I'll plug that into the one up top. So we get 4k minus 2 is equal to k, which means that 3k is equal to 2, k is equal to 2/3. And if k is 2/3, m is equal to 2k, m equals 4/3. Okay. For 10, we're giving some kind of a description, graphical and algebraic, about something that is continuous but not differentiable. We actually saw a good example of that, where y equals sine inverse of x, and y equals ln of x plus pi over 2, where when we did the algebra for that, that didn't come out at that point, and graphically what we saw was something that looked like this and like that, where this was not a nice clean line. Function whose derivatives are equal at x equals b, but is not continuous. So I might do something like e to the x minus 1 and e to the x plus 1. And at 1, where this thing would be split, what you'd end up seeing is that we have something that looks like this, where you'd have the same slope at these points, but they wouldn't be touching because they'd be shifted apart from each other. That's what's going on with the plus one and the minus one. It's splitting up those pieces. And again, this would be like for where x is less than 0, where x is greater than 0, or something like that to make that happen. Neither continuous nor differentiable at x equals c. Well, all we need to do is do something that's not continuous here. So I might do one of my favorites, which is the absolute value of x over x, and maybe even make this x minus c over x minus c. What this ends up doing is giving us a graph that has a negative part and a positive part, and ends up looking something like this. A function that is continuous everywhere and differentiable everywhere. One of my favorites is e to the x, because that is a nice exponential, and its derivative is also e to the x, so it's nice and smooth everywhere.